Hello SFT students, welcome to the first video that will be an attempt to be a concise video to quickly go over this. Please watch this and then as you watch it or after watching it or in between many viewings of this video, I hope you can complete the worksheet that is you'll see shortly. So the video will assume that you're familiar with the common English definitions of the following words: object, speed, motion, distance, time. Not asking for a technical definition, just a general idea of what I might mean if I use that word. The video will assume you are at least a little familiar, novice level, with some formal physics math definitions of the following: motion map, distance, displacement, area, slope, units, rate. If you're not watching this video, we'll familiarize yourself with these things because they're not too tricky. The video will assume you can formally define, understand, and explain the following technical terms. So a moderate to expert level understanding, or orange or black belt, or whatever we want to end up using. No expectations, intentionally left blank. We don't have any formal definitions of anything yet that I expect you to know. Here are some things, some goals. I hope you will get a better understanding of speed, velocity, time, positive direction, negative direction, slope, area under a curve, units, m meaning meters, s meaning seconds, m/s meaning meters per second, and rate. I do not expect you to get expert level, but I expect that you have some idea of formal ways of these. Notice that some words appear here, speed, and down here, speed. Speed means different things in regular conversation and in physics. So you got to kind of understand their different definitions. So on to the actual sheet, which will be appearing shortly. Alright, so this is what the sheet looks like at first, and I'm going to do pretty much every other problem, and I want you to do the problems that I don't do, and I will explain this as concisely as I reasonably can. So motion maps and velocity versus time graphs. Note this is velocity graphs. That's different than what we did before. Before we did motion maps. We'll have to do some motion maps too. Or what I mean is, sorry, position versus time graphs is what we looked at before. So notice that this word here is not called position, it's called velocity. That's something different. And if you don't know what that word is yet, I have not defined it. I hope you will get an understanding for what that word is through this video. So first let's read the instructions. Sketch velocity versus time graphs and motion maps corresponding to the following descriptions of the motion of an object. Okay, a motion map. Well, first, before I can do that, I need to read the description. And in each case of these, there's going to be kind of three things. There's a written description, a motion map, and a graph. And you'll be usually provided one piece of information. It won't always be the written one, and you'll be expected to be able to construct the other two, since they all say the same thing. The object is moving in the positive direction at a constant steady speed. That means that it's moving away from zero and positive. It's getting a bigger and bigger number. I can start it wherever I want. I've been given no instructions. I'm going to choose not zero because I don't have to choose zero, so I'm going to not choose it. And I'm going to make an arrow, and that's the start of my motion map. Alright, now I'm going to put a dot there because this is what a motion map is. It shows dots with arrows, showing how this thing goes. And now this is number line has not, these units are not defined. A unit would be, here's meters, but these ticks, so tick one, these ticks, doesn't say how many is a tick. I get to pick because it hasn't been told what they are, so it's up to me to fill in the blanks. I'm going to be simple here and say that's 1 meter, that's 2 meters, that's 3, that's 4, that's 5. I do not always have to put the m here, as long as it's defined either here at the origin or I at the end in parentheses put an m saying all those are meters. Okay, so what I've described here is an object that started at 1 meter and then was at like 2.5 meters a second later. If I define each arrow as a second, which I haven't, but that's what we're going to assume. We're going to assume that each dot is a second. So a second later was about here and was moving that way, and a second later was across here. Important thing here, constant steady speed. that means that this arrow and this arrow and this arrow should all be the exact same length. Now, did I draw them all with the exact same length? Probably not. I didn't use a ruler. I didn't use copy and paste. So I'm going to use this dash, which is used in geometry, to indicate congruence or equivalency. For example, if I draw a triangle in geometry and I want to say all three sides of this triangle are equal, I put a dash, one line through each one. That means that this line, and this line all have the same length. If it's more complicated and I have a triangle like this, and I want to say that this side and this side have the same length, I can do that. If I don't put a line there, it means I know these are the same length, that's a different length. So I'm going to use congruence dashes to indicate, yes, all three are the same length. So what does that mean now for my velocity time graph? First, I want to erase what I drew here. I don't erase that much. I'll leave that there. All I'm going to say is that, well, velocity, I'm not going to define it yet. I'm just going to draw it. So what is it saying? It's saying that the velocity was positive because this line here we assume to be 0, and our units would be meters per second. And it's positive. It's going in the positive direction. And it's always staying the same, so I'm going to put some ticks here. So it's second 1. Again, it's time. If I define time here in seconds, I do not need to put 1 second here. I can put a 2 here, and I know it's seconds because it's defined on my axes. 3, 4, 5. Okay, so I know at second 1, what was the velocity? Well, I'll put a number here. It looks like what I drew was about 1.5. It looks like it's moving about 1.5. Well, I'll just say 1. And you can argue with how sloppily I drew that, but I'll say it's 1. Okay, so what this means is at second 1, at second 0, the object was moving at 1 meter per second. At second 2, 1 meter per second. At second 3, 1 meter per second. It agrees with this. I'm going to do the object is standing still, because I think that'll be useful. So an object standing still, again, doesn't matter where it started. I'll have it start right here. And we're in meters here, and I am going to label these because otherwise it's confusing, potentially. And I'm going to, again, say every dot is going to be a second. So I'm going to say it starts at 4 meters from the origin and stays there. So here, how much time have I shown? I've shown 1, 2, 3, 4 seconds. So I'm actually going to be careful about that here. Time is in seconds. And I have 0 seconds here. I have 1 second here, 2 seconds here, 3 seconds here, 4 seconds here, 5 seconds here. And on my velocity, I'm going to have, here are positive numbers, and here are negative numbers. Quick question to think about, if I have a line up here, first off I want to delete that because there should be, that was just my plus getting too big. Positive number, that would mean an object is moving away. A negative number means an object is moving toward the origin. And that is not a full, complete definition. But that is a good thought right now. So if an object is standing still, what does that mean? That means that it's not moving. It means it has 0 velocity. So on the y-axis here, where is 0? Well, if here it's positive, here it's negative, 0 is right here on the line, unless I define it otherwise. So I'm going to have to use a thick line. So I'm going to make my pencil, or maybe I'll use a marker. And I think that line will be thick enough. And I'm going to make it a different color. And I'm going to show that, well, at right here, well, how fast is the object moving? From between seconds 0 and 1, it's not moving at all. I'm not going to kind of cross that out. Change my mind, I'm not going to cross it out. Between second 1 and 2, which is here, still at 0. Between second 2 and 3, still at 0. And I'm not going to make this blue line go any further. And I'm going to clear up a bit. Oops. I can't go too far. I really don't want to go past 3 because I don't know anything about past 3. Now if I read into this that I assume its object is standing still forever, then I can go like this forever. The object is never moving forward or away from the origin. Now I do include more information here than I do here because it's easier to include information here. So I don't want to draw thousands of dots. I could have this go off to infinity, and I would have to draw infinite dots. It's much easier to do on a graph. That is why we will not be using motion maps forever. We'll be using them as little as possible until we just agree what they mean. Okay, 1 second. I'm going to let you do number 3 and 4. Give them a shot. If you get them wrong, again, it's, the point is we will then discuss in the class. So I'm going to now bring up a few more problems on the worksheet. I expect you to fill in the ones that I do here. That's going away. And here comes some problems on the next page. I'm missing a little bit of information that is important, which is the instructions. Okay, the instructions for the second page of this document or worksheet are to draw the velocity time graph for an object whose motion is produced by the position versus time graph shown below at the left. And this is a bit tricky, and I'm actually going to do this, and then I'm going to show you a program, several programs that you can go on your computer. One is a download, one is a website that will help you do this. Because basically, this is fundamentally, we are actually now studying calculus, even though you're never going to hear that word uttered in the text because it scares people. But physics was invented, sorry, let me edit that out. Calculus was invented because of physics. Isaac Newton, father of modern physics, also inventor of calculus. That is not a coincidence. And he was more a physics guy than a math guy. So calculus is just so freaking useful for doing physics that you have to do calculus in physics. We might not call it calculus, just to make you feel better, I guess. But anyway, this is very much similar to a calculus problem. That doesn't mean it's hard, but it will take some time to do. So draw the velocity versus time graph for an object whose motion produces position versus time graphs shown below at the left. So let me draw a line here to indicate the difference between these. So let me first look at these two graphs. Again, these are representing the same thing. Here on the left in red, here I've got a position time graph. How do I know? Because that says position, and on the y-axis, the x-axis says time. Here I've got another graph. I'm going to show in blue. And what do I know about this graph? I know it's a velocity time graph because velocity is on the y-axis and time is on the x-axis. Surprisingly, time on both of them is on the x-axis. Time will always be the x-axis. So, all right, what happened in the first second here? Well, in the first second, the object moved from, first second is going to be this blue line. And how far did our object move? Well, it went from 0 meters. It went up to 2 meters. So what is the total distance? The distance is defined as the final position minus the initial position. And I'm going to bring up a little calculator here, or some Mathematica. And I'm going to define that. I'm going to do this symbolically. Hopefully that will be helpful. So I will have x final. So where did that object end up? It ended up at 2. And what was my x initial? Start at 0. Little formatting. Then let me make these numbers a bit bigger, or I'm going to zoom in here. So this is big and easy to see. I could add units in here, and in this case I will, because it will not 0 meter. I have to use the same exact word, so let me just use M. That's simpler because that's more like what you would write. And then what is the definition of velocity? Well, velocity, well, first I'm going to enter this. And I'm going to do some things here that are code, so please just ignore that. Velocity. The definition of velocity is x final, which means the final position, where did it end up, minus the initial position, divided by the amount of time that took. And in this case, we're always going to be using 1 second. So I'm just going to be doing 1 second. Let's see what it says. It says 2 meters per second. Now I could format that a different way, but that means this is the same as, exact same as it's saying 2 meters per second. Okay. So I'm going to make that go away. So what does that mean? It means I look at my velocity time graph, and during the first, between second 0 and 1, the velocity was 2. So I'm going to line here. What about between second 1 and 2? Well, here basically you may realize I'm just calculating slope. Between second 1 and 2, well, it looks like it went up by a half. Now, I don't like making guesses if I don't have one of these lines, so I'm going to go over by 2 seconds and see that if I go over by 2 seconds, I go over by 1. Why do I prefer to do that? It's because I know I can see that right there that at 3 seconds it was at position 3. Or I could go over 2 more seconds, because it looks like this line isn't changing. It's a straight line. So I'm just going to, for simplicity's sake, I'm going to say that over this line, let me change the color, make this even more clear. I'll do it some orange. If I take this line, over this number of seconds, between seconds 1 and 5, it went up. The position went up by 2 meters. And how long is this? Well, it's 1 second, 2 seconds, 3 seconds, 4 seconds, 4 seconds. So now let's find, this maybe seem pretty clear to you, but maybe not. So what is my final position now? My final position here is 4 meters. Now initial position, now do not, this is a place where you might think it should be 0, but here I'm basically asking 2 questions. For the first second, this was my initial, this was my final. For my new question, this is my initial. My initial here is already at 2. I could define final and initial different ways, but basically every time I ask myself a question, I am redefining my initial and my final in order to make this velocity equation work. So I'm going to redefine those two. So now my velocity is defined as final position minus initial position. It'll be using these numbers, and I want to put in the right number of seconds. How long did it take for this between this final position and initial position? It took 4 seconds. So I'm going to put 4. So I'm going to delete this. I'm going to hit enter. There should be no big surprise here. It's m/2. That might be a little tricky to read, but that is exactly the same as 1/2 meters per second. Or if you don't like fractions, 0.5 meters per second. So that means I'm going to go to my graph. I was graphing in blue. I will continue to graph in blue. Where is a half? It's about here, and that's the second one. Put a little dot there, and we know this through second 5. So this is my graph. Interesting question here. Do I draw a line, a vertical line here? I'm not going to answer that. I'm going to let you think about it. Right now, this is a perfectly acceptable answer. If you drew a vertical line, well, the way I've drawn this, we'll talk about it. Okay, question 8. For many graphs, both the slope of the line, slope needs to be defined, and the area between the line and the horizontal axis have physical meanings. What do the slope of a position time graph tell you about the motion of an object? Looking at the velocity time graphs, determine the units for square of area on the graph. I'm not going to answer these, but I will define slope and I will define area right now, because otherwise these two questions are impossible. So I'm going to bring up something blank, define slope and define area. So first, slope and area. Hopefully those words will appear. Actually, I'm going to do this over here. I could have been slightly more efficient here. Sorry. So slope, first I'm going to plot a graph. I'm going to plot first I'm going to define a function. If you don't know what a function is, that's cool. Don't worry about it. I'm going to find a function that says that it's just going to be a line of the form mx plus b. That's the equation for a line. And I'm going to say that my slope is 2 and my v value is 1. Actually, no, I'm not. I'm going to do something fancier. I'm going to write a little thing. I'm plotting this function that is going to be a line between starting at 0, going to 10 and 1, tick marks of 1. And I want to be able to change the slope between, let's say, -1 and 1, and ticks at 0.1. I feel confident in this because I'm thinking about getting this program for the entire school for a while, really, and seeing if that's useful. And then I want to be able to change my b value from say -5 to 5 in increments of 1. Let's see if it does that. Whoops. I'll make mistakes under the high pressure of the microphone. There we go. Oh, how embarrassing. What do I do wrong? Oh, I see. Yeah, sorry. You did that all over. And I'll maybe just speed this up so you can see. I feel like it's been a few months since I've used this one. You don't use it, you use it, lose it. There we go. About time, Mr. Reinhardt. Jeez, I'm the worst. Okay, so here's, I can change m. This is slope. This is me changing the slope. And I will show the numbers. This is a large slope. I want to be able to show more slope. So I'm going to go actually have my slope be, let's say, go from -2 to 2. And so that's fine. This is B. This is my y-intercept. That means the point where it hits the y-axis. That's the y-intercept. So notice if this number is 2, it's going to hit here at 2. If this number is 5 or 6, because I hit 6 instead of 5, oh, I don't want to play it. I want to say 5 and go to 6. Now it's intersecting at 6. If I want to intersect at 10, that. I'll intersect at 10. If I want to start at 0, I'll hit enter. There it is, right at 0. Okay, the slope value, I can make it a positive number if the slope is 1. That means every second it's going to go up by 1. If I make it 2, it means every tick. It's not seconds, I didn't define it as seconds, that's just what the example we're using. So if I go over by 2, this should go up by 2. So with this b value of 0 and this m value of 2, I'm going to talk about the slope and the area of this curve. So let me copy and paste this thing. Put it over here, and then define slope and define area. Okay, so here we go. Slope is defined in algebra as rise over run. It could also be defined as the final x position minus the final initial position divided by the final y position minus the final initial y position. I like to define it as delta x over delta y, which is this symbol, a triangle. And I apologize for my handwriting using this tablet. And in English, this means how much did x change divided by how much did this y change. So for this particular example, let's look at this line, and that's my final point. It's my initial point. How much did it change? I'm going to use a green line. So first of all, just some little note taking. That's my x-axis. That's my y-axis. Between these 2 points, to start in the beginning, how much did it change? Well, in the x, it went from 0 to 5. So my change in x is 5. How much did my y change? My y changed from 0, and it ended up at 10. So it changed by 10. So my slope here is 1/2. There are no units because I didn't define this as meters or seconds or whatever. I didn't define it at all. It is just a slope of 1/2. What is the area? Okay, well, I've got here a line. If I take my final point and drop a line down, there is an area under this curve. And let me use some sort of device to do this. Kind of fill that in. I want to paint it black because I see a red door and I want to paint it black. So what is the area of this shape that I'm now drawing in? You may notice that, hey, that's a triangle. That's a triangle, Mr. Reinhardt. In case you don't know, the area of a triangle is the area of a triangle. It's important you know what shape you're talking about. Is 1/2 base times height. Okay. Well, 1/2 times base times height. Well, that's 1/2. What is the base of this triangle? The base really doesn't matter what you define as the base. Typically, you'll define this part as the base. It's just as long as you don't do the same number twice. The base is 5. 5 what's? In this case, nothing. It's 5 numbers. It's 5 numbers long. And what is the height of this triangle? The height is 10. Okay, so little math. 1/2 times 5 times 10. What is that? You can use a calculator. I don't mind. I know that 5 times 10, that's 50, and half of 50. So I'm doing this in the way that makes this problem as easy as possible for me. Whoops. Got ahead of myself there. 5 times 10 is 50. 1/2 times 50 is 25. So the slope in this case is 1/2, and the area is 25. If we were to go and now put some units in here, well, this area would have to have a type of units, and the slope would have a different type of units. Okay, that'll do it.